As we are working with functions, we need to remember that functions are designed to model the real world. And in the real world, there are limitations to our inputs and our outputs. For example, if we were talking about the value of the stock market over time, the time is your input and the value is your output. Well, the time is probably in some type of range. Maybe your graph covers the past 10 years. So we're limiting our number values to the past 10 years. That is the idea of domain and range, is we're looking at what limited values we have on our inputs and our outputs. Let's start with some definitions. First definition is going to be domain. The definition of domain is simply all the possible inputs into the function. The second word we're going to define is range. Range is all the possible outputs of a function. Now, as we're looking at this idea of domain and range, the inputs and the outputs, there are several ways to express these limitations on the inputs and the outputs. One way to express it is with an inequality, which uses symbols like less than or equal to, greater than or equal to. Another way to express the domain and range is with what is called set builder notation. The idea of set builder notation is we have these squiggly brackets with whatever our variable is, a vertical line, and then some type of limitation listed. We'll look at some examples of what this looks at in just a minute. And the third way we often express these limitations is with what is called interval notation. Interval notation uses a range of numbers between parentheses or between square parentheses with different meanings. And we'll talk about those meanings here in just a minute. So for example, if we wanted to express the idea of being between 6 and 9. Now that's not really clear. We're going to have to probably look really close and decide, can it be 6 or 9, or is it strictly between? For example, we might be interested in it being neither 6 or 9, just between them. Well, let's look at what this would look like as an inequality. As an inequality, the way we show that something is between 6 or 9, let's use the variable h. We put less than symbols on each side of the h, showing that it is between 6 and 9. And that would be the inequality showing that the h is between 6 and 9. Set builder is very similar. What we will do with set builder, though, is we'll kind of formalize and say h is the variable, and then use a vertical line, and then the same inequality, 6 is less than h, which is less than 9, with the squiggly bracket. Now in interval notation, we're going to use square and curve brackets to show the limits of the range. We're going from the numbers 6 to 9. So we'll put a comma between them. And then to show that we're not equal to either of them, we use curve brackets to show that it's equal to neither of them. Now if I change things and say it could be 6 or 9, we just need to make a minor change. In the inequality, we still say the height is between the 6 and the 9, but to show that it could be equal to 6 or equal to 9, we put a little line beneath the inequality. The same adjustment is made in set builder notation. 6 is less than or equal to h, which is less than or equal to 9, and close the brackets. In interval notation, we show this difference with a square bracket. When we put square brackets around the 6 and 9, then we say it could be 6, could be 9, or anything in between. We could even mix these and say 6 is a yes, but 9 is a no. So it could be 6. So we'll show that as an inequality with or equal to, but not 9, so we just show the less than. You'd see that same thing in set builder notation. H such that 6 is less than or equal to H, which is less than 9, but not equal to 9. And in the interval notation, we can mix these brackets and use a square bracket for 6, saying it's okay to be equal to 6, and a curved bracket for 9, showing that we don't want to be equal to 9. What if I just wanted to show below 9? Not 9, just strictly below 9. If I wanted to be below 9, then we would say the H is just below 9. I'm not going to use the or equals to because it can't be 9. Set builder notation would be similar, H such that H is below the 9. But then in interval notation, we're going to do a comma 9, and we can use a curved bracket for the 9 because we're not actually equal to 9. But I can be anything below 9, and to show that I can go to anything below 9, we'll use this symbol for negative infinity. And because you can never actually be equal to infinity, it will always get a curved bracket. So similarly, if I wanted to be above 6, and we're going to go ahead and say it could be 6. Now we can use our H, and we're going to use the opposite direction, greater than or equal to show it could be equal to 9. And then in set builder notation, H such that H is greater than or equal to 9. Or in interval notation, we're going to have 9 comma positive infinity. Because I can be equal to 9, we'll have a square bracket on that, but we can't be equal to infinity ever, so infinity always gets a curved bracket. And we could really mix this up and combine several inequalities together. Let's try saying below negative 3, but not negative 3. Or between 2 and 5. And when we say between 2 and 5, we're going to say it could be 2, but not 5. Well, for the inequality, the first part says below negative 3, so we'll say H is less than negative 3. Not actually equal to negative 3. And then to show we're going to do a second part, we just write the word or. And then we say between, so the H is between 2 and 5. And that builds what we call a compound inequality by using the or in between. In set builder notation, it would be H such that H is less than negative 3, or 2 is less than H, which is less than 5. And actually, we said it could be 2, so we should be or equal to on the 2. In interval notation, though, we're going to do something different for the word or. Watch what we're going to do for this. So for the less than negative 3 part, we're going to go to negative 3 with a negative infinity at the bottom. And the way we show or with interval notation is we use a capital U. And then we're going to say it could be equal to 2, and we're going to go up to 5, which it cannot be equal to. So that kind of goes over how we can express these domains and ranges, or these limitations on our inputs and output values. But we spent a lot of time talking about that. Let's look at how we can actually do what we want to do. Let's look at domain and range from a graph. First example, let's start with an example of some application. Let's look at energy use. And let's say energy use has been graphed where they have 1990 up to 2020. And let's say it starts down here at 700, so we've got years on the bottom. And we're talking about 700, maybe kilowatts, 800, 900, and 1,000. And it's going to start here in 1990 at 700 kilowatts, and maybe each month it goes up or down until it stops up here in 2020 at 100 kilowatts. When we say domain, we're interested in what are the possible inputs. Inputs come from the x-axis. The years are our inputs. Outputs come from the y-axis. The outputs are the kilowatt hours. So if I wanted to look at the domain of this graph, domain would be all the x values. So if I start with my graph, I see my graph starts at 1990 and it kind of goes down the graph to this peak. The end of the graph where the graph actually stops is in 2020. So I could say my domain goes from 1990 up till the year 2020. And that would be interval notation using square brackets. But what if I was interested in the range? The range of this graph are all the possible outputs. If I start at the bottom of my graph, I see my graph goes out from 700 to 1,000, because range is the y values, how far up we're going. So the range is going from 700 kilowatts to 1,000 kilowatts. That would be the list of possible outputs, the range. Let's break this down a little bit more with some simpler graphs just to make sure we've really got a good handle on it. Let's take a look at this graph. And I'm going to put a solid dot here at -3, 1, solid dot at 0, 3, and an open dot here at 2, 2. And then I'm just going to kind of connect them with a little curve. Now, a little brief note that I should add, when we use a solid dot, that means it can be equal to. When we use an open dot, it means it's not equal to that value. So that can help us decide if we're using square or curved brackets. So when I ask about the domain, we're going to read the graph from left to right and see what x values it hits. Notice it starts here at an x value of -3. And it can equal -3, so I'm going to do a square bracket. Then as I go down the graph across the domain, it's equal to all of these values until it stops here, where x is equal to 2. Now it's an open dot, which means it can't equal 2, so I'll do a curved bracket. For the range then, we're going to do the same thing, but we're going to look at the y's instead. Looking at the y's going from the bottom to the top, I see the graph starts here at a y of 1. Square bracket because it's a solid dot. And then the graph goes up to a top point. And at the top of the graph, it hits the number 3. 3 up. So the graph is going to stop at the top of the graph at 3. So the range says it's going from 1 to 3, up and down. And the domain says we're going from -3 to 2, left to right. That's how we can pull the domain and range off of a graph. But what if we just had a function? What if we want to find the domain from the function formula? Well, usually it's easier to kind of start by thinking about what is not allowed. So for example, if I have f of x equals 2x squared minus 3x plus 4, we're looking at what's not allowed to go in for our variable x. Well, what I see is happening here is one of the x's is squared, but I can square any number. We're multiplying by 2 and negative 3. We can multiply by any number we want. And then there's some adding and subtracting that happens with the 4 and the other terms. We can add and subtract any number that we want. So with this expression, I could plug any number I want into the x, and there would be no problem. We would say that is all real numbers. Or in interval notation, we would be going from negative infinity to positive infinity. In other words, I can plug any number in for x, and I will get an answer for this expression. Now that doesn't always happen. Let's look at the function f of x equals 3 times the square root of 4x minus 1 plus 2. Now something to note with this problem that's different is we have a square root. An important thing to know about square roots is square roots can't have negatives. In other words, this part under the square root, the 4x minus 1, has to be greater than or equal to 0. Because we can't have negatives. If it was negative, we can't take the square root. So I can solve this equation by adding 1 to both sides. 4x is greater than or equal to 1, and dividing both sides by 4, and x is greater than or equal to 1/4 becomes my domain. I could write that as interval notation, saying that x can go from 1/4 up to as big of a number as it wants. And because we have or equals to, we're going to do a square bracket for the 1/4. Let's do one more example before we wrap up. Let's look at f of x equals 4x over 3x plus 9. Now something to be aware of here is 0 cannot be on the bottom of a fraction. In other words, this part on the bottom of the fraction cannot be 0. So the 3x plus 9 cannot be equal to 0. And I can solve this by subtracting 9 from both sides, meaning 3x cannot be negative 9, and dividing both sides by 3, x cannot be negative 3. Now, if we were to put this in interval notation, we'd be good with any number all the way down to negative infinity, all the way up to negative 3, but we can't be negative 3. So we'll do a curved bracket for negative 3. Then we'll do the union to represent a second part, and we can pick up just after negative 3 all the way up to infinity. And notice this interval notation includes every number except for when our x is equal to negative 3. That's how we can look at the domain and range of functions, what values we're allowed to use for inputs and outputs in our functions. Take a look at the practice assignment to try a few on your own, and we'll see you in class.